This is video 2 for the electricity and magnetism unit. The easiest way to remove electron energy is simply from the friction caused by the electron flow. Such friction is what we call electrical resistance. Now, if we think in terms of water, this would be like letting water go through a pipe versus having a bend in a pipe. This would create more resistance because it would create more friction in the water itself. Some metals, such as tungsten, have a lot of resistance. The filament of an ordinary incandescent light bulb is made of tungsten. So when current flows through it, the resistance heats up the filament enough to make it glow. The wires in your toaster are also made of tungsten. The wires in your oven are made of tungsten. So as electricity flows through that tungsten, the friction causes it to get really hot, and the heat gets to a certain point where it begins to radiate or glow. Now, one way we have of calculating resistance is with this formula right here. Now, in this one, resistance, first off we have this rho, which is called resistivity. And that comes down to the material. So tungsten has high resistivity, copper has low resistivity. So that depends on the material. A longer wire is going to be more resistive than a shorter wire. So a lot of the electricity we produce in the U.S. is lost to the fact that, well, we have such long wires carrying the electricity from a power plant to where it's being used. A is for the cross-sectional area of a wire. A big, thick wire is going to be less resistive than a thin, skinny wire. In fact, if you use wires that are too thin and you put too much current through them, they will actually get really hot and burn up. So those are the three things that affect resistivity, especially in wires. Now, materials that conduct electricity very well are called conductors. Materials that do not conduct electricity very well are called insulators. Now this leads us to something called a fuse, or a circuit breaker. The wires in your house are made out of copper, which is low resistance, so they have that low resistivity. Rho would be a small number for it. If the current is high enough, however, these copper wires do have enough resistance to get hot and could start a fire in the walls of your home. So to prevent this, houses have a device that limit the current in the copper wires in your homes to around 15 amps. So what a fuse is a short length of high resistance material, and it's designed to fail. When the current flowing through it reaches a certain point, the wire, because of the resistance, it gets really hot and it melts, and it stops the electricity from flowing through it. So once it breaks the current, once it breaks the wire, the current stops flowing, and then you simply have to replace the fuse. We say the fuse blows. There are many different types of fuses. You see them in everywhere from calculators to digital multimeters. You see them in computers. You see them in homes occasionally. We don't really see fuses in homes anymore because it's kind of expensive to keep replacing them. We have switched to something called a circuit breaker. So in your house, instead of having fuses, you'll have a circuit breaker. And this is two metallic strips that are fused together. And when it gets hot, it starts to bend in a certain direction. And that you'll hear a popping sound, and that then stops a current. Once it cools, you can reset it. And the nice thing about that is that it's reusable. A fuse, once it blows, you have to throw it away and buy a new fuse. A circuit breaker, you can use it over and over and over again. So here is a quick little design of a circuit breaker. There's a lot going on to it, but basically all you need to know is that once the current reaches a certain value, the circuit breaker stops electricity from flowing through the wire. And again, the purpose of this is to protect your home, because if the current reaches a certain value in your home, it can potentially start a fire in your home. So in this little graphic over here, it discusses the differences between fuses and circuit breakers. Just take some time and read it. It's not too much, but I'll let you take a look at that. All right, so we've talked about current and we've talked about resistance. The next topic is voltage. And what a volt does is it measures the electron energy. So amps will tell you how many electrons are flowing past a point each second. Ohms, which is resistance, measures how much a material will try to slow down those electrons. And then volts will tell you the energy of the electrons. The energy unit that we use is called the electron volt. So 1 electron volt is 1.6 times 10 to the negative 19th joules. That number should look familiar. That's the same as the charge of an electron. There's a reason for that. So, a calorie is a typical amount of chemical energy for a gram of material. The electron volt is a typical amount of energy for a single atom or molecule. So, if I have an electron in an atom, its energy is right around 1 volt. TNT, so dynamite, its energy per molecule is right around, again, 1 volt. A flashlight battery, it's right around 1.5 volts. In the United States, your house wall outlets, it's right around 110 volts. The voltage in Europe is regulated to be a little higher than it is in the United States. So in Europe, it's 220. If you had an old television set, 50,000 volts. We'll discuss how you can go from 110 volts to 50,000 volts later, but there is a device that'll do that for you. An alpha particle. So going back to our radiation, it's very high energy. It's 1,000,000 volts. So then, low volt electrons are not very dangerous, such as like a flashlight battery. It has a typical voltage of 1.5 volts, so it produces electrons with an energy of around 1.5 volts. So you can hold a device, that battery in your hand without any danger. So let's talk about something else, static electricity or finger sparks. So you've probably done this before. You put on some socks, you walk through some carpet, then you shock somebody. Those sparks that sometimes fly from your finger to a doorknob or another person, we call that static electricity. And this occurs because as your feet rub against the ground, the electrons come off of the ground and stick to your body. These electrons are static. They are stuck to your body until you encounter a good conductor. For that spark, the voltage was probably somewhere around 40,000 to 100,000 volts. And that seems like a lot. But it doesn't kill you. It doesn't hurt anybody. And the reason for that is because the current is low. And the reason why is that you're not really picking up a lot of electrons as you rub your feet against the floor. It's a very, very small number of electrons that you pick up. So to know the power, the destructiveness, you need to know the energy per particle and the number of particles per second. So before we get to that, here's just some graphics here showing you how you can pick up static electricity. And again, a lot of it comes from rubbing. So you're ripping electrons from one object and placing them on another. And then you can produce some static electricity. All right, so electrical power. The electrical power delivered by electrons depends on the energy of the electrons and the number of electrons per second that arrive. The first is voltage, the second is current. So if we multiply these two numbers together, we get power. So power, electrical power, equals the current times the voltage. And the units for this will be watts. So an amp times a volt equals a watt. So we can do a quick little calculation. So let's do this calculation. The power equals current times voltage. So that's going to be 1 volt. I'm sorry, 1 amp. Times 1 volt. So this power then equals 1 watt. Very, very simple. Here's another practical example. Suppose we have a light bulb. A light bulb uses 110 volts because that's the voltage to your house, and it carries a current of 1 amp. So it pulls 1 amp from the wall. So doing this calculation, so we got 1 amp times 110 volts, that equals 110 watts. Power also equals energy per time. So energy must equal power multiplied by time. So I can then do a calculation of 110 watts. And let's say this thing is left on for 1 hour. This equals 110 watt hours of energy. Or real close to 0.1 kilowatt hours. The electric company then will charge you for how much energy you use. And typically, 1 kilowatt hour will cost you right around 10 cents. So we can see that running that light bulb for 1 hour is going to be like maybe 1 cent. Okay, so note then that high voltage does not always mean high power. If the amps are tiny, then a high voltage can be safe. So that's why the sparks from a Van de Graaff machine or the sparks from someone shocking you is not dangerous. The energy then in like a finger spark and lightning. We can do some calculations now. So when we take a look at the energy of electrons from finger sparks from static electricity, we see that it's around 40,000 volts, maybe more. But there are not very many excess electrons on your body, so the current is usually like 0.2 milliamps. So that's 0.25 times 10 to the negative third. It's low enough to keep the power low, because power, and since power is energy per unit time, energy is power multiplied by time. So during, when you're shocking somebody with a finger spark, it takes roughly 1/1000th of a second for the excess electrons to leave your body. So when we do these calculations, energy is power times time, and power is current times volts. So when we do all this, we find that the energy during a spark, so when you're shocking someone, is right around 0.01 joules, 2 millionth of a food calorie. So that's very, very, very low. So, in contrast, let's take a look at lightning. Lightning is very similar to static electricity on a much, much greater scale. So during lightning, both the voltage and the current is high. So the voltage is around 10 million volts for a lightning bolt, and the current is around 100,000 amps. So let's do the math for this. So energy equals power times time. Power is current times voltage. So I take that and times that by time. So the current is 100,000 amps. The voltage is 10 million. Now the time for a lightning bolt is 30 millionth of a second. So that's 1 divided by 30 million. And the second goes over here. So that means that the energy during a lightning bolt is 33,000 joules. Comes out to right around 8 food calories. Still doesn't seem like a lot of energy, but that might help explain why some people are able to survive a lightning strike. All right, that will conclude video 2.